I think for anyone who first see this beauty, the most outstanding part of her is her eyelashes, which still stand out today.
4,000 years ago, someone with straw red hair and a felt hat was laid to rest in the heart of a Chinese desert. She is one of hundreds, naturally dried by salt and drought until her eyelashes survive, and she wears the exact wrong face for the place. Tall, high-nosed, deep-eyed, dressed in Central European plaid. For a century, the answer seemed obvious. She was a traveler. But in 2021, her DNA said the exact opposite. She never arrived. She stayed, and beneath her feet, the desert was hiding something even bigger. Ghost Faces of Xiaohe. The name Taklamakan is often translated from Uyghur as the place of no return, or more colloquially, you go in, but you don't come out. It is a brutal, shifting expanse of hyper-arid sand dunes, scorched by blistering summer heat and frozen by bitter winter winds. It is one of the most inhospitable, dry places on the surface of our planet. Yet, at the dawn of the 20th century, explorers navigating these desolate wastes stumbled upon a scene that looked less like a graveyard and more like an impossible ship graveyard in an ocean of sand. They found Xiaohe, the small river cemetery. It wasn't a collection of traditional stone tombs. Instead, it was a massive, terraced sand dune bristling with a forest of cleared poplar posts, shaped like oars, driving vertically out of the sand. When archaeologists began peeling back the layers of earth, they found dozens of boat-shaped wooden coffins. Each hull was wrapped tightly in raw ox hides, which had dried and shrunk over the millennia, sealing the contents in an airtight, vacuum-packed capsule. When those skins were sliced open, scientists weren't greeted by skeletal remains or crumbling dust. They were staring at people who looked like they had simply fallen asleep an hour ago. Among them was the woman who would become known across the world as the Beauty of Xiaohe. She was laid to rest around 1800 BCCE. Because of the unique cocktail of hypersaline soil, extreme dryness, and the vacuum seal of the ox hides, her body had naturally mummified without any of the invasive embalming techniques used in ancient Egypt. Her skin was intact. Her long, delicate eyelashes were perfectly preserved, casting soft shadows on her cheeks. She wore a beautifully crafted, conical felt hat adorned with feathers, a string skirt, and a woven woolen cloak fastened with a wooden peg. And she was smiling, a faint, serene expression frozen in time. But as the dust settled, a massive academic argument exploded. Look closely at her face, or the face of the Beauty of Lulan, found nearby, and something immediately feels out of place. They didn't possess features typical of East Asian populations. They were tall, with prominent, high-bridged nasal bones, deep-set eyes, and hair that ranged from light brown to a striking straw red. The woven woolens they wore featured distinct plaid and twill patterns that looked like they were plucked straight out of Hallstatt-era Central Europe or Celtic Scotland. For more than 100 years, the archaeological consensus felt utterly airtight. This was an open and shut case of long-distance migration. The narrative went like this. A group of Western pastoralists, likely early Indo-European speakers from the Eurasian steppe or the mountains of Siberia, embarked on an epic, generational trek across thousands of miles. They brought their sheep, their weaving traditions, and their Western looks, eventually settling down in the isolated oases of the Tarim Basin, more than 1,000 years before the formal establishment of the Silk Road. The only real debate left for historians was figuring out exactly which route they took to get there. Then, in late 2021, an international team of geneticists decided to stop guessing. They extracted and sequenced the whole genome data from 13 individuals from the Xiaohe culture and 5 individuals from the neighboring Dzungarian Basin, dating back between 3,700 and 4,100 years. Everyone expected the results to confirm a Western or Siberian origin. Instead, the data completely broke the traditional historical timeline. The genetic analysis revealed that the Tarim Basin mummies were not foreigners at all. they carried absolutely zero genetic ancestry from the Yamnaya steppe herders, zero from early European farmers, and zero from neighboring East Asian populations. Instead, they belonged to a highly distinct, genetically isolated lineage known as the Ancient North Eurasians, or ANE. To absorb how profound this is, you have to realize that the Ancient North Eurasians are essentially an evolutionary ghost population. They were a widespread group of hunter-gatherers who thrived across Siberia and parts of Europe during the peak of the last ice age, some 25,000 years ago. As the glaciers retreated and populations shifted, the ANE genetic footprint drastically shrunk, mixing into other groups until they virtually vanished as a distinct, unblended population everywhere else on Earth, except in the Tarim Basin. The people of Xiaohe weren't weary travelers who had just completed a cross-continental migration. They were the direct, unmixed descendants of this ancient Ice Age lineage. They had been living right there, along the rivers of the basin, for thousands of years, while the rest of the world shifted around them. Their distinct physical features weren't Western faces that had wandered into the wrong continent. They were simply an extraordinarily old, ancestral look that had been preserved in genetic isolation. But this discovery created an even bigger paradox. Usually, when a human population is that genetically isolated, marrying almost strictly within their own small lineage for generations, their culture is equally isolated. They tend to stick to what they know. Yet, the Xiaohe mummies proved to be some of the most culturally open, cosmopolitan innovators of the Bronze Age. Despite keeping their bloodlines entirely separate from outsiders, their graves were a treasure trove of global ideas. They grew wheat and barley, crops that originally came from the Fertile Crescent in the Middle East. They cultivated broomcorn millet, a grain domesticated in North China. They utilized dairy pastoralism, a lifestyle adopted from the steppe herders to their north, and they buried their dead with ephedra, a medicinal desert shrub used across Asia. They were sealed off by blood, but wide open by culture. They sat at a geographical crossroads, acting like a cultural sponge, interacting with every merchant, herder, and traveler who passed by, actively choosing what technologies to adopt, while consciously choosing never to intermarry. They weren't travelers who arrived at a destination. They were the ultimate survivors who stayed put, adapting seamlessly to a changing world until their oasis home finally dried up. But how did an isolated Ice Age population manage to sustain a booming, agricultural oasis lifestyle in the dead center of a hyper-arid desert wasteland in the first place? An ocean under the sand. The secret behind how those ancient oases even existed comes down to a massive geological trap. It is ringed by some of the tallest mountain ranges on Earth: the Himalayas, the Tian Shan, and the Kunlun Mountains. For millions of years, as glaciers on those peaks melted, rivers ran straight down into the basin, carving out the vibrant green river valleys that the Xiaohe people called home. But as the climate shifted over the millennia, those rivers shrank, evaporated, and swallowed themselves into the earth. The surface became a dead, bone-dry wasteland. But a few years ago, geologists studying the basin's deep structure noticed something completely baffling. They were tracking carbon dioxide levels in the area, and the math wasn't adding up. In normal carbon models, deserts are supposed to be carbon neutral or even net positive emitters. Because there is very little vegetation to photosynthesize and trap carbon, whatever CO2 is in the air just floats around or seeps out of the dry soil. But in the Tarim Basin, carbon dioxide was vanishing. Vast quantities of the gas were disappearing into the environment, and nobody knew where it was going. It was a literal geographic missing puzzle piece. So scientists decided to look down, way down. Using deep Earth imaging, seismic tracking, and structural modeling, they discovered an anomaly that should be physically impossible given the desert above. Deep beneath the Taklamakan Desert sits a subterranean aquifer so massive that it defies comprehension. Preliminary estimates suggest that this hidden underground reservoir holds up to 10 times more water than all 5 of the North American Great Lakes combined. Let that sink in for a second. Underneath one of the driest, most brutally parched landscapes on the surface of the planet lies a giant pitch-black ocean. Now, before you picture a pristine, crystal-clear underground sea where you could drop a well and drink your fill, we have to look at the chemistry. This isn't fresh water. If you managed to pump it up to the surface, you couldn't drink it, and you couldn't use it to water standard crops. It is a highly alkaline, intensely salty brine. But that exact hostile chemistry is precisely why it is one of the most important environmental discoveries of our generation. Because this water is so heavily packed with alkaline minerals, it behaves like a massive chemical sponge for carbon dioxide. Here is how the loop works. Over thousands of years, melting snowpack and heavy rains from the surrounding mountain ranges washed down into the basin. As that water traveled, it dissolved massive amounts of minerals from the rocks, turning highly alkaline. At the same time, as it filtered through the soil and into the deeper layers of the earth, it absorbed immense amounts of carbon dioxide from the atmosphere, trapping it in the liquid. Eventually, this heavily carbonated salty brine sank deep into the subterranean fractures of the basin, locking the carbon away from the atmosphere. Scientists call this a carbon sink, and the Tarim Basin's hidden ocean is doing heavy lifting on a global scale. It is estimated that this single underground reservoir absorbs roughly 20 billion kilograms of carbon every single year. To put that into perspective, that is equivalent to the annual carbon emissions of several million cars, completely neutralized by a silent, invisible process happening miles beneath the sand. It completely changes how we look at deserts. For a long time, the global scientific community viewed places like the Taklamakan as empty voids, barren, static landscapes that contribute nothing to the Earth's active climate regulation. Now we know they are dynamic, breathing ecosystems that are actively scrubbing our atmosphere from the inside out. But identifying a massive underground sea is one thing. Actually, utilizing the unique biology of the desert to fix the broken, blowing sand on the surface is a completely different challenge. If a hidden ocean can trap carbon beneath the Earth, could scientists find a way to make the shifting dunes on top stay completely still? The 10-month living crust. If you've ever tried to build a sandcastle, you know the ultimate problem with sand. The second it dries out, the wind destroys it. Now, multiply that problem by a few million square miles. In the deserts of northern and western China, shifting sand dunes aren't just a scenic backdrop. They are an active environmental threat. Strong desert winds push these massive walls of sand outward, swallowing highways, burying railway tracks, and choking nearby cities in apocalyptic dust storms. For decades, the only way to stop a moving sand dune was an incredibly slow, back-breaking engineering method called straw chessboards. Workers would manually push straw grids into the sand, creating a checkerboard pattern that disrupts the wind just enough to keep the sand from blowing away. It works, but it takes an immense amount of time, and it relies entirely on dead organic matter that eventually rots away. To truly fix a desert, you need biology. You need something alive that binds the sand together. In nature, this happens through a process called desert succession. Over hundreds or thousands of years, specialized microorganisms like cyanobacteria, mosses, and lichens slowly colonize the surface of the sand. They secrete sticky sugars that glue the loose grains together, eventually forming a dark, fragile skin over the desert floor known as a biological soil crust, or biocrust. Once a biocrust forms, it acts like armor. It stops wind erosion, traps moisture, and creates a nutrient-rich foundation where real plants can finally sprout. The catch? In a harsh desert environment, waiting for nature to build a biocrust can take up to a century. Scientists at the Shapatu Desert Research and Experiment Station looked at that timeline and decided it was way too slow. They asked an audacious question: can we manufacture a living crust in a lab and apply it like paint? The answer turned out to be an engineered breakthrough that sounds like science fiction: soil seeds. Scientists began harvesting specific strains of indigenous desert cyanobacteria, hardy, single-celled organisms that have survived in the desert for millennia and breeding them in massive liquid biostimulant tanks. They mixed these superbacteria with a liquid blend of microalgae, polymers, and organic nutrients to create a thick, paste-like inoculum. Then, they went out to the shifting dunes and literally sprayed this living liquid across the sand. What happened next stunned the ecological community. Under normal conditions, these cyanobacteria would struggle to survive the intense heat and UV radiation. But the engineered mixture provided just enough artificial shade, moisture, and initial nutrients for the bacteria to wake up and get to work. Within just 10 to 16 months, the sprayed sand underwent a transformation that normally requires 50 to 100 years. It formed a thick, resilient, fully functioning biological soil crust. This engineered living skin completely altered the physical properties of the dunes. Testing showed that the new biocrust reduced wind-driven sand erosion by a staggering 95%. Even better, because cyanobacteria are photosynthetic, they began pulling carbon dioxide directly out of the air, converting it into organic nitrogen and enriching the barren sand below. The crust acts like a moisture trap, holding on to the rare drops of desert rainfall instead of letting them instantly drain away into the deep sand. With the shifting dunes locked down and the soil artificially jump-started with nutrients, the desert floor was no longer a hostile void. It was ready for life. But locking the sand in place was only the first step of the experiment. With a stable foundation secured, scientists were about to witness an even more baffling anomaly, this time involving the massive man-made forests planted directly into the desert heat. The accelerated supergrowth. Once you use engineered biocrusts to lock down the shifting sand, the next logical step is to bring in the heavy artillery of ecological engineering: trees. For nearly half a century, China has been working on the largest artificial environmental project in human history. It is called the 3 North Shelter Belt Program, though most people simply know it as the Great Green Wall. The goal is staggering: plant a massive 2,800-mile barrier of billions of trees stretching across the northern wastes to completely block the advance of the Gobi and Taklamakan deserts. For decades, critics argued that this plan was a fool's errand. Conventional ecological wisdom states that if you plant trees in a hyper-arid, nutrient-depleted environment, they will grow at an absolute crawl, stunted by the brutal heat and lack of water. But when researchers from Peking University began conducting long-term, comprehensive biomass audits of these massive man-made forests, they uncovered an anomaly that threw the traditional textbooks out the window. The artificial forests planted directly into the desert fringes weren't struggling. In fact, they were thriving at an accelerated rate that seemed biologically impossible. The data revealed that these human-planted desert forests were accumulating biomass and growing up to 66% faster than equivalent, undisturbed natural forests located in more temperate zones of China. It was a total physiological paradox. How could a tree planted in the brutal, parched soil of a desert border completely outpace a tree growing in a lush, naturally watered valley? The answer lies in a highly complex, modern phenomenon known as the CO2 fertilization effect, combined with a hyperspecific evolutionary defense mechanism. Trees eat carbon dioxide. Through photosynthesis, they pull CO2 from the air and use solar energy to snap those molecules apart, turning the carbon into wood, roots, and leaves. Because human activity has pumped record amounts of carbon dioxide into the global atmosphere, the baseline food supply for plants worldwide has dramatically increased. But in a standard, dense natural forest, trees are packed tightly together. They are constantly competing with their neighbors for sunlight, root space, and soil nutrients. Even if there is plenty of carbon in the air, a natural forest tree is often bottlenecked by its crowded environment. In the desert shelter belts, the layout is entirely different. Scientists space these trees out precisely using a highly optimized grid system designed to maximize the limited underground water usage. Because they have minimal competition for sunlight, and their roots can spread out laterally across the sand without hitting a wall of rival root systems, They are perfectly positioned to exploit the excess atmospheric carbon. Furthermore, because desert environments are blasted with an abundance of intense, unfiltered sunlight, these trees are operating at maximum photosynthetic capacity nearly every single day of the year. When you give a tree unlimited sunlight, clear physical space, and an atmosphere heavily enriched with carbon dioxide, it essentially goes into a state of hyperdrive. The trees absorb the excess carbon far more aggressively than anticipated, packing on dense wood and expanding their canopy at a breakneck pace. This supergrowth turned these artificial forests into incredibly high-efficiency carbon vacuums, pulling millions of tons of greenhouse gases out of the sky far faster than any climate model had predicted. But while these engineered forests and living crusts are successfully taming the borders of the wasteland, the deepest, most extreme interior of the desert remains a realm ruled by pure physics. Deep within the dune fields, far beyond where any tree could ever take root, sits a landscape of giant, towering structures that don't just defy the wind, they actually make noise. How do you explain a desert where the dunes reach the height of skyscrapers and the sand itself literally starts to sing? The sonic sand and the megadunes of Badain Jaran. If you want to see just how far desert physics can stretch into the impossible, you have to leave the river basins behind and head east to the Badain Jaran Desert. This isn't just an ordinary patch of sand dunes. It is home to a surreal landscape of geological giants. Here, the sand doesn't just form small, shifting ridges. It rises into massive, towering structures known as megadunes. Among them is Bilutu Peak, the tallest stationary sand dune on the face of the Earth. It rises more than 1,500 feet from base to crest, making this single mountain of sand taller than the Empire State Building. Under normal circumstances, a sand dune that tall shouldn't be able to stay in one place. The wind should constantly erode the peak, shifting the grains and leveling the structure over time. Yet, these megadunes have remained completely stationary for thousands of years. When geologists began drilling deep cores into these sandy skyscrapers to figure out what was holding them together, they discovered an unexpected secret hidden inside the architecture of the dune itself. Deep beneath the dry, baking surface layer of loose sand lies a permanent reservoir of moisture. Even though it almost never rains in the Badain Jaran, deep atmospheric water vapor and ancient underground spring water seep up from the bedrock below via capillary action. This moisture creates a damp, cohesive core inside the dune. The dry sand on top acts like a thermal blanket, preventing this internal water from evaporating into the scorching air. This hidden wet core acts like a solid internal skeletal system, anchoring the entire 1,500-foot structure firmly to the earth and allowing it to withstand the most brutal desert gales without washing away or migrating across the plains. But the sheer size of these dunes isn't the only thing that defies explanation. If you climb up the steep, windward face of a megadune and slide down the slope, or if a strong gust of wind shears across the crest, the desert will suddenly do something eerie. It will begin to sing. This isn't a faint whistling sound or a trick of the wind. It is a deep, resonant, low-frequency drone that can reach up to 105 decibels, loud enough to sound like a low-flying propeller plane or a roaring choir of heavy machinery vibrating straight through your chest. Marco Polo famously encountered this phenomenon during his travels through the Asian deserts, attributing the terrifying, disembodied noises to malevolent desert spirits. Today, physicists have stripped away the spirits and replaced them with a fascinating display of acoustic fluid dynamics. For a desert to produce booming sands, a highly specific checklist of physical conditions must be met simultaneously. First, the individual grains of sand must be incredibly uniform in size, perfectly round, and completely free of dust or organic debris. In the Badain Jaran, thousands of years of relentless wind have meticulously sorted the sand, polishing each grain into a smooth silica sphere. Second, the sand must be completely bone-dry on the surface. When a layer of this dry, polished sand is disturbed and begins to slide down the face of the dune en masse, it sets up an effect called a shearing layer. As millions of identical grains slide over one another, They don't move smoothly. They bounce up and down, colliding thousands of times per second. Each individual collision creates a tiny, microscopic sound wave. Because the grains are all the same size and moving at the same speed, these millions of tiny sound waves don't cancel each other out. Instead, they lock into perfect synchronization, magnifying one another. The air gaps between the moving surface layer and the solid, damp sand core beneath act like the hollow body of an acoustic guitar, resonating and amplifying the sound until the entire 1,500-foot dune transforms into a massive, booming subwoofer. It is a stunning reminder that even in the most lifeless, dry expanses of the interior, the desert is an incredibly fine-tuned mechanical system. But understanding the pure physics of stationary megadunes and singing sands is a luxury that modern engineers has only earned after surviving decades of brutal ecological warfare. Because before scientists figured out how to collaborate with the desert's natural forces, they tried to conquer it with raw brute force, and the resulting collapse nearly ruined everything. The modern green wall collapse and rebirth. When you look at the lush, carbon-devouring forests of the Great Green Wall today, it is easy to assume that eco-engineering is a flawless science. But nature has a brutal way of correcting human arrogance. Back in the early phases of the 3 North Shelter Belt program, engineers didn't understand the delicate balance of desert hydrology. They rushed in with a brute force mentality, treating the desert like an empty plot of land that just needed to be colonized by trees. They planted hundreds of millions of identical saplings, mostly fast-growing poplar and willow trees, creating massive artificial monocultures. For a few years, it looked like a resounding success. Green canopies stretched across the horizon where nothing but yellow sand had existed for centuries. But beneath the surface, a hidden ecological time bomb was ticking. Because these trees were all the exact same species and planted at an unnatural density, they required an immense amount of water to survive. They began aggressively drinking from the desert's fragile, shallow water tables far faster than rare rainfalls could replenish them. By the late 90s and early 2000s, the water tables completely collapsed. Deprived of moisture, billions of trees died simultaneously across northern China, leaving behind vast fields of gray, brittle tinder that actually accelerated soil erosion instead of stopping it. To make matters worse, an outbreak of the Asian longhorned beetle tore through the weakened, identical forests, wiping out entire sectors of the wall in a matter of weeks, because there was no biodiversity to slow the insect down. It was a catastrophic, multi-billion-dollar reality check. Scientists realized that you cannot force a forest onto a desert. You have to build an ecosystem that respects the laws of aridity. This failure forced a complete revolution in how China approaches desertification. Engineers threw out the old playbook of planting dense, thirsty trees and replaced it with a highly sophisticated, data-driven methodology. Today, the project relies heavily on low-water native shrubs like Haloxylon amodendron, Saxaul, and Caragana korshinsky. These plants don't grow into towering leafy giants, but they possess massive, deep-reaching root systems that lock down the soil while using a mere fraction of the water that a poplar tree requires. Furthermore, the entire planting process has been completely modernized using automated technology. Instead of sending armies of workers into the blazing heat with shovels, scientists now deploy custom-engineered, GPS-guided desert vehicles and drones. These machines roll across the dunes, automatically injecting seeds into the sand at precise depths and intervals calculated by AI algorithms that analyze local soil moisture and wind patterns. They weave these native shrubs into complex, staggered grid patterns that mimic natural desert scrublands, ensuring that the vegetation never outdrinks its environment. By shifting from an aggressive invasion of the desert to a precise technological collaboration with it, the modern shelter belt has found its footing. It proved that human ingenuity can indeed push back the sand, but only if we work within the rigid boundaries of the desert's natural laws. And as we look at how these engineering triumphs mesh with the ancient history buried in the sand, we find ourselves standing at a strange crossroads where the past and the future meet. The shifting sands of time. The discoveries unfolding across these arid expanses shatter our oldest assumptions about what a wasteland can be. For centuries, the global imagination viewed the desert as a static void, a lifeless graveyard where rivers go to dry up and history goes to be forgotten. But from the perfectly preserved eyelashes of the Xiaohe survivors to the massive, carbon-absorbing ocean locked deep beneath the burning dunes, we are learning that the sand is not an empty space. It is a highly dynamic, hyper-efficient archive of the planet's past and a testing ground for its future. By looking past the harsh, deceptive surface of these environments, modern science has unlocked a completely new ecological framework. We now know that the deepest deserts can sing with pure physical precision, that engineered microbes can compress a century of soil evolution into a single year, and that human technology can successfully push back the sand if we learn to respect its rules. The Taklamakan and Gobi are no longer just symbols of geographic isolation or environmental threats. If you want to keep uncovering secrets hidden in the most unexpected places on Earth, hit that subscribe button.